On to our center of mass examples. So let's take our first one here. We have a crescent wrench. Now this crescent wrench is an irregular solid, we would call it. It has 3 dimensions to it, and we might sense that this end is heavier than this end, so that the center of mass might be closer to this end, and so forth. But now let's imagine we take this wrench and we throw it. And as we throw it, you might imagine it's very difficult to throw that thing without getting it to rotate, and that's because when we're holding on to it, we're grabbing this end. Well, if the center of mass is here, we would have to throw it holding it at the center of mass to prevent it from spinning. But in any case, we usually throw it at the end, and in doing so, it will rotate. But we know this object should follow a parabolic path, but yet it's got to be more complicated because this thing is now spinning. Well, now let's imagine that we shrink this entire wrench down to this one point. Consider it to be a point object. This system of molecules in this wrench we are now going to treat as one point. And when we throw it with this initial velocity, it will indeed follow the parabolic path. It's the center of mass that will follow that parabolic path. So despite there being this complex motion of the rotation, we can study the path of this thing by treating it, reducing it, the system, to a point object. The principles will act on the center of mass of the system, and we know how that center of mass will behave. And another fun example here, we could take a diver, and we know that competitive divers, they'll dive, and then they'll rotate and tuck, and they'll have different speeds. They might even do twists, sideways, in and outs, and all their kind of crazy things. Nonetheless, if we find the center of mass of this diver, the center of that mass of that diver will remain on that parabolic trajectory, no matter what else is going on with their body. Another application of center of mass, let's take the Earth-Moon system. So here we have the sun, we have what we think of as the elliptical Earth orbit, but in reality there's the Earth, and the moon goes around the Earth. Well, there is a center of mass somewhere between the Earth and the moon, like so. And it is that center of mass that will follow the elliptical path around the sun, not the Earth itself. The Earth itself will not stay on that path. It's the center of mass that will remain on that path. And so for that reason, this drawing that I've selected here is actually not correct. The Earth should actually be offset a bit, and the center of mass should be right there. This is a little bit easier to understand if we take what's called a binary star orbit. Now, binary stars are systems of stars that revolve around a center of mass. Oh, a center of mass. Here is star 1, here is star 2, and they revolve around each other. Kind of. What they do revolve is around the center of mass. Now, it turns out binary stars are about 60% of all stars. Just sort of a fun fact here. So when we look up in the sky and we see stars, about 60% of them are actually double stars. Our sun, a single star, is actually a rarity. It's not common for there to, it's not as, nowhere near as prevalent to find a single star as there is a binary star. But if we trace this out, what we see happening is this star is traveling like this, and this star is traveling like this. But what they are all both doing is revolving around a center of mass. Now again, what we could do is we could say, let's treat this system not as these two stars, but as one giant body that has the mass of both of those stars. The center of mass of this system stays fixed in this location. So wherever this yellow star is, wherever it is, let's say it's here, the other star, the blue star, must be in a place to balance it out so the center of mass stays there. And this can be even crazier. This one here, I want us to imagine like we had the shoot and drop where the fellow had he had a rod like so, and there was a spring, and one ball drops and the other one was fired. So I want us to think about that there is a rod between these two balls, and there is a spring, but it's actually attached to this ball and this ball. So if we take these two and pull it like so, we pull them apart and release them, this spring will go back and forth and back and forth. And so the distances between these will change. And when this moves closer, this one will have moved closer. But at all times, the center of mass will be right here. Center of mass will be right there. Now, even if we were to give this a spin like so, even as these are contracting back and forth, like you see here, getting shorter, shorter still, the center of mass will stay on its path. Now, in this case, what we have here is kind of we're modeling two charged or magnetic particles that could come together and fly apart, and they're traveling around, say, the nucleus of an atom, right? That's what we're depicting here. So its path that it wants to travel on is a curved path because of the dynamics of an atom. But these two bodies, magnetic particles or electrical particles, might be coming in closer, back and forth, such that the center of mass stays the same. And even if this system is rotating, as it appears this is rotating as it travels around this orbit, the center of mass will stay fixed on that path. It is part of a system. These two blue objects are part of a system that are tied together in their system, behaving according to particular laws and rules, which are related to each other and related to this central body. And so if we replace these two blue bodies with a red body of equal mass, it will move according to the center of mass of that system. In other words, the center of mass of this system is behaving and following certain rules as it travels in this orbital path. No matter what's going on, that center of mass will continue to follow that direction. So it makes sense to be able to simplify this system and study the behavior of the center of mass rather than the individual objects. So those are some cases. Now let's look at another one here. Here we have a center of mass. We can take this firecracker or this bomb and treat it as a point object. A point object is where all mass is located at the center of mass. So we could replace this bomb with just this point where all the mass is. Now, we might say this bomb is sitting there and the velocity is 0. That's the center of mass. When this bomb flies apart, the center of mass will remain in the same spot. This particle is moving along that path, that path, that path. Each of them is moving on their own paths. Like so. But that center of mass that was represented by the object before it blew apart is in the same exact location as it was beforehand. Remember, we know the law of inertia, which says an object does not want to accelerate. Well, this body is not accelerating. All of these individual pieces accelerated, but the center of mass has a velocity equal to 0. So the center of mass will have a velocity equal to 0 after the explosion because of the law of inertia. That is not intuitive. Now let's take this further. We know how these two-dimensional type projectiles go. So we have a firecracker that is fired like so. The center of mass represented by the red dots, is moving along this path. It's a projectile. Now, while it's moving along, it explodes. But that entire system, which consists of the firecracker and all its pieces, this is the system. So the firecracker, the bomb is the system. This bomb, all of its pieces, is still the system. And so this system now, the center of mass, will continue to follow that trajectory. Even as these particles are expanding outward over time, the center of mass will continue to follow that projectile path. And those are some examples of center of mass. If we understand these examples and apply them to lots of situations, we will be in good shape with center of mass.